My name's Nick Zeeb. I work at a company called LMAX Exchange. As the name implies, it's an exchange. We trade currencies, and the challenge for us is to do that very fast. The faster we do this, the better prices we get from the banks, and the better prices we get from the banks, the more people come and trade on our exchange. So, as it says there, speed creates good price, which is also important for reliability. So, for us, latency is really, really important, and speed is. My name is Nick Zeeb, and I'm one of the Java developers there. Right, so the component that I'm going to talk about, I'm just going to explain the problem briefly. The problem itself isn't the main thing I want to get across. This is just the example we're using here to show some of the principles. So the issue we're solving is that if you have a buffer that holds a bunch of things, in this case, the example is you've written your own trading system. It's sitting on your computer over there, and it's going to make you shitloads of money. It's going to be amazing. The only problem is you're connected to an exchange on the left there, and the exchange pumps out prices very, very quickly. And here you have some well-known technology stocks represented pictorially and their share prices. Now, at any point, you have an input buffer to your system of prices you need to process to try and find bargains, which you're going to use for your trading system. And yeah, you have this buffer. Now, what happens is before you've finished processing, before you've even gotten to an old price, which you haven't even processed yet, of Red Hat here, the Red Hat price changes. And you, as your trading system, does not care about any old prices, right? You can't trade on this anymore. It's gone. So if this buffer is growing with old prices in it, you're wasting time and computing power. So what you really want is, before you even get to processing this, is that as soon as this guy arrives over here, the new price comes in, you instead replace in the buffer at exactly that point the old price. You never have to deal with it, and the buffer can never grow beyond the size of the number of symbols. So that's what we want to solve. We call it a coalescing buffer. It's not just for prices. It has a generic interface, which I'm about to show you. Just some background. There were a few requirements. It had to be thread safe between two threads, the producer and the consumer. The updates had to come in the right order, as we've seen there, with the exception of how you update prices. And because the processing in our case was idempotent, a very small number of duplicates is acceptable to improve performance. So just a quick picture here. This is basically a data structure that's like a collection. It has a size, a capacity, ask if it's empty or full. And here's the interesting bit, right? You can offer into this collection a new key with a value. And what it will do when you offer this, it'll try and scan the collection to see if it can replace an existing one. If so, it replaces it, and it stays the same size. Otherwise, if it can't, it puts it on the end. And there's the consumer interface as well. You can provide a collection, and you say, give me all the elements, or you say, give me at most these many elements. So that's what we want to design, something that implements this interface. OK, so how do we do it? How do we go about it? Well, we use TDD. TDD is useful, and obviously, as I'm sure you guys all will know, the slogan is, all code is guilty until proven innocent. So let's try and prove some innocence. Let's start with functional tests, right? I mean, this is a very basic thing that we all do. We have a bunch of things that it should do that are important, the basic things. You know, you put things in it, you don't lose things, you update things correctly, blah, blah. We know all these things. And of course, they're all failing in the beginning because we haven't finished it. So that was one of the requirements. Another one is that because it's a buffer, we can't afford to have anything like memory leaks, things like that. So that's not something people often test for. So we had to think about how we can do that. And the way we did it, we came up with several solutions, but this one was the simplest. What we do is we create a magical value. We create a value and a key type of this as well. And we put a counter in it, and basically we count to see how many items are garbage collected. We put them all in, we drain the buffer, and we call system GC, we wait a little bit, and we make sure they're all cleaned up. So that will show us whether everything's garbage collected correctly, which is nice. Right, thread safety, another important aspect of what we're doing. Again, something people don't often test for, and it's actually quite hard to test for thread safety. But nevertheless, it'd be nice to have at least a go and try. So what we did was we wrote a test, and this is the producer. Basically what it does is, as fast as it can, with some very large number of updates, puts in two values, a first value and second value for the same key. So it's always overriding the previous one, and it's doing it as fast as it can. And the hope is that if there are threading bugs, because this is happening so quickly and it's always updating, that we would hopefully see some problems. Now, random aside, there is a problem with testing, right? How many tests do you need to run to make sure that you have no bugs, right? It's the same problem as philosophers call induction, right? How many white swans do you have to observe to prove that all swans are white, right? Unless you can observe all swans that are ever going to exist in the universe, you can't actually prove it completely, because unfortunately, a single observation, such as the one we made when we discovered Australia, shows that the entire theory is false. So really the point here, which is the example stolen from Nassim Taleb, is that you should always keep a healthy amount of skepticism when you see testing results. So tests are good, but they can never prove that code works, right? Without inspecting the generator, by just looking at the outputs of tests, you can get more and more confidence that something works, but you can never prove it. And for the threading test, that's especially true, right? I can run this 1, 2, 3, blah, blah, a million times, and the millionth time, boom, it fails. So just keep in mind, be skeptical. You can't ever prove that it works completely. You can just get more confidence. Right. If you can remember one thing in this last talk of the day, I know you're tired, it's this bit, right? We're supposed to be doing something called computer science. And at the end of that term is this word science, right? And the idea of science is that we're supposed to measure things, right? We come up with a theory, and then we check whether that theory is right. This seems surprisingly simple, but at the same time, in my career, I've come across plenty of people who have a bunch of mantras or things they've collected along the way that they believe to be true because people who sounded intelligent told them they were true. And they may be true, but they haven't tested them, right? Things like, this framework is lightweight, or garbage collection is cheap, or all sorts of things that are out there. They might be right. But unless you've tested and measured it, we don't really know what the answer is. By the way, I've never, ever discovered a framework that's not lightweight, or a heavyweight framework. If anyone's ever seen a heavyweight framework, please tell me. So the point is, again, be skeptical, go and measure things. And when it comes to designing for performance, that is the biggest thing to take away here, is that it seems obvious, but not enough people do it. Go and measure all the assumptions that you have in your head, because some of them may be wrong. So how did we actually come up with the performance test for our component, which is in the middle here? So what we do is we pin on one core the producer that's going to pump a bunch of values into the coalescing buffer. And on another core, we're going to drain this buffer as fast as we can, and we're going to measure how long it takes to get all the values through this to here. So when you design a performance test, one very, very important thing is what load are you going to put into this test? When you put values in the buffer, what values are you going to put in? What's the distribution of those values? What do they look like? Because this is really important. If you get this bit wrong, the entire design will be wrong. Whatever you choose here to put in as your input to your performance test is what you're going to be designing for. You will repeatedly measure how it performs given the load you're about to come up with here. So think very carefully, measure in your system what your load actually looks like, because if you get it wrong, the entire design will be wrong afterwards. So what did we do? You remember in the beginning we showed a few examples of different stock prices that came in. But of course, in general, the keys could be anything, right? They could be messaging topics, they could be whatever you like. And in our case, we had a load profile that looks a bit like this. And this is quite common. I've seen this in a lot of systems, that you have this kind of Pareto ratio. In a lot of messaging systems, what you have is a dominance of a few topics here. In our case, things like updates to the Eurodollar. They absolutely dominate all other, well, them and a few others like them, will absolutely dominate what the system does. And, you know, some events like, oh, the end of day has occurred, will occur only once a day. Well, if everything's working correctly. So basically, think very carefully what the load of your system looks like, and make sure you get that right in your performance test. So what we've done here, like I say, is to pick a Pareto ratio. We have some dominant topics. So this is a good term. It comes from a racing driver called Jackie Stewart. He was a 3 times Formula 1 champion, and he came up with this term, mechanical sympathy. Now, he believed that the best racing drivers don't necessarily need to know how to build an engine to drive a race car, but they have enough of an understanding of how one works in order to work in harmony with that engine, right? And I think in computing, something similar is true. If you want to get the absolute best out of your hardware, you need to have a little bit of an understanding about how it works. You don't have to go and dig your own copper out of the ground. You don't have to go and solder all the transistors together. You just have to have a basic understanding of how it works. So what I want to do today, in the next few slides, is pop the hood. Let's have a look what's actually in a modern architecture. and how can we use it to our benefit? So here is our system stack. So we got our friend the Duke, we got the Penguin in our case, and we're running in the example here on this test on my laptop, which is a Core i5 processor, and it can go up to 2.6 gigahertz, which sounds pretty good. So what have we got here? Notice here at first I have 2 physical cores that can run a maximum of 4 hardware threads. So we know this thing is hyper-threaded. So be a bit careful about that. You don't actually have 4 cores. You have 4 virtual cores, and they're being shared. You only have 2 real ones. Another thing to be careful of is, do you see here the clock speed actually says 1.7 gigahertz? Well, hey, what's going on, right? I paid good money to get 2.6, so why is it saying 1.7? What's that about? Well, if you look at it, the 2.6 figure that Intel are quoting here is the max turbo frequency, which sounds pretty cool, sounds like it comes out of Knight Rider, and it basically does. What happens if you look closely at what this max turbo frequency is, it is an unsustainable rate at which your processor can run, but not sustainably. So if the current consumption is below a certain amount, it's not getting too hot, and it thinks it can overclock it for a short period, then it will do that. But you have no control over this. It will decide, based on these factors here, whether it's going to do this or not do this. This is a complete nightmare for performance testing, because it means your hardware architecture is just randomly being overclocked sometimes. And when you run your performance test, you get a number, and this is a good thing to check your performance test. Run the same test again. Do you get the same number? Because if you don't get the same number, there's something wrong with your test. You're testing some bit of noise. You're testing the turbo clocking on your chip, or you're testing the garbage collector, or there's something wrong with your test. So when it comes to testing with a processor that has this ability, you must switch it off, because otherwise you will get non-repeatable results, and you can't trust any of the results that come out of it. So again, you have to be aware of what the thing's doing. Some other tips about performance testing. I'm sure everyone is aware of this, but I'll mention it again. Don't litter, right? If you're running a performance test and the test itself creates a reasonable amount of garbage, you're probably only testing how bad the garbage collector is. That's not what you want to test here. So have a look. When you run your performance test, see if there's any garbage collections going on. If they're because of the thing you're testing under test, that's okay, because that's part of the algorithm. But if it's the test itself creating garbage, then you probably have a problem. One other thing to be aware of. Do you guys see this car here? This is what your JVM looks like when you start it up in server mode, right? It is frozen cold. Do not take this car and drive it around the racetrack and decide, oh, it's really slow. No, that's unfair, right? When you start up your JVM, especially in server mode, it starts off in interpreted mode. It's profiling. It's looking at what you're actually doing. And only when it has a few examples, or enough examples of what you're doing, will it then make runtime decisions about how to do the just-in-time compilation. So keep an eye on the just-in-time compile steps happening as you're running your test, because only when they've finished is it fair to test it. So yeah, don't drive that around the racetrack. Just a bit of XML, which is of course a great language to do any kind of programming or scripting in. How do we do some of these things I just talked about? So here are a couple of things. Our friend, the max turbo, can be disabled by setting the clock frequency, pinning it basically to the frequency you want. What else do? We task set the system so it runs on actual physically separate cores. Remember, it claims it has 4 cores, but they're virtual cores actually shared. There's only really 2 independent cores inside your chip. So you pin them to the real ones so you can test it concurrently. Make sure, keep an eye on the things we just said. Make sure that your compilations have finished by the time you do the actual testing. Keep an eye on the garbage collector. Sorry, this is a specific case in our test. We set the compile threshold to be a bit higher because the way that we're running this test is that we run it so fast that slight differences in thread timing means it can make wrong compile time decisions. That wouldn't happen in your real code because you wouldn't run it this fast. Because this is obviously going flat out, and slight variations in thread timing create weird optimizations, so we just made that 10 times bigger than it normally is. But yeah, if you get very strange results in your performance test, it may be that if you're using multi-threaded, that the optimizations are very different based on thread timing. So we can talk about that later, but that was the specific thing we had to deal with here. Right. if you're going to remember two things about this talk, remember the first one was we're supposed to be doing computer science? This is the other one. Design, as my ex-colleague Trisha G always reminds us, is a process, right? It's not a thing you do once. It's not a thing that some architect does in some smoky room or whatever else. It's not something you write in stone. It's a process that you go through. You start with an idea, and then you implement the idea, and then you measure that idea. If it's a good idea, you keep it. If it's a bad idea, you throw it out. And you go around this loop several times until you're happy with what you've got, right? And I want to take you through a couple of iterations of our thinking of how we built this thing. So, at least the screen's big enough to show a bit of code. I know it's late, but hopefully you'll follow along a little bit. So what's the simplest possible way that we can implement this interface? Basically, the simplest possible way is to use a linked hash map to preserve ordering. When you put something in it, when you offer a new key, you check, have we got this already? If so, I'll just update it, I'm done. If not, it means I've got to grow my structure, so you have to check that you haven't reached the capacity yet. And if that isn't the problem, then you can put it in there and you're done. Notice here the thread safety is achieved by using the synchronized keyword, which is putting a big fat lock around the data structure. And the poll looks very similar. We acquire the lock, and we pass in the collection, and we fill it, and we return it back. So the next thing we do is we measure this. So how well does this do? OK, we get 25,000 operations per second, or 25 COPS, which is reasonable. It's where we started. Let's see if we can do any better. Let's try some other ideas. OK, who's read this book? Anyone read this book? OK, that's not enough people. We need more people reading this book. It's a good book. One of the ideas in this book I talk about is the idea of using compare and swap operations, CAS. In this case, why don't we try and have a go at that? Let's try and represent the entire state. The aim here is to get rid of the synchronized statement. So we can represent the entire state in this atomic reference. And what happens is when we try and offer a new key, when we try and put it in here, we have to get that reference. We have to clone it, because you can't modify the reference because it may be being used down here. And then you do exactly what we did before, and then you try and do a compare and set. We change the modified one with the current one. And if you fail, then that means this guy got in your way, and you've got to do it again. And here, the code here basically has to grab it, and in one atomic step, you have to get and set it from the existing one to a new one. OK, so that's CAS. Let's measure it. CAS is supposed to be good, right? Let's see what it does. Uh-oh. That's 100 times slower. That wasn't good. What went wrong here? If we look back for a second, it turns out this is a very good test for your garbage collector. What you're doing here is you're cloning this reference for every single thing you add, and that just destroys, well, that absolutely creates a huge and humongous amount of garbage. Now, the lesson here is not to say, oh, CAS is slow, CAS is always slow, never use CAS, CAS is evil. No, wrong. CAS is sometimes very good. It's just for this particular problem, it didn't help us. It made it worse. And we didn't just say, oh, we know CAS is fast because everyone says CAS is fast, therefore we don't even have to test this. No. We took an idea, we tried it, and it didn't work in this instance. And we can see that because we have a test. We can run it. It tells us that was a bad idea. OK, let's try something else. And do you remember we were talking about the idea of mechanical sympathy, that to get the best out of your system, you have to have a little bit of an understanding of what's actually happening underneath in our hardware. So let's have a look at a modern architecture diagram. This is Intel Sandy Bridge, but the concept is general enough that it exists in AMD and Ivy Bridge and Haswell and all this stuff. Basically, the problem has been, over the last years, is that these guys up here, the actual hardware cores, can run really fast. They are getting faster and faster, although we're hitting some limits with CPU frequencies. But there's actually hardware parallelism going on inside the cores nowadays as well, so they are still getting faster. The problem is the speed with which you can access memory, your DRAM out here, has nowhere near kept up with how fast these guys are. So a lot of the time, what you can get is that these guys are just waiting. They're doing nothing. They're literally just waiting for someone to come back from the warehouse on the other side of the planet over here to get the one bit of data they needed. And that can be really slow. That can really slow down your stuff. If you look at, you can look at some of the cache hit ratios on your operating system to see how well your system is doing. Because, sorry, what I should say is, what modern processors have is they have this memory hierarchy. You have memory that has different sizes and different speeds. So you have, closer to your cores, you have an L1 cache here, which is very fast. It takes, on the order of a few cycles to access, but it's also very small, typically something like 64 kilobytes. Then you have the L2 cache, which is a bit bigger and a bit slower. Again, they are specific to the individual cores. And then you have a shared L3 cache for the particular socket. In our case, we don't have a second socket. You could have a second socket using the quick process interconnect, but forget about that. We're looking at only one socket at the moment. And you have a shared L3 cache, which is, again, bigger and a bit slower. And then you go out further and further and further up until you get to somewhere here, which is much longer than accessing data here. Now, the key thing to realize here, and this is the important bit, is that data in your memory hierarchy here does not move around in a single bit or a single byte. What it moves around in is these sets called cache lines. So imagine you're all sitting in rows here. If I need to speak to one person in the front row, I don't just ask that one person in the front row to come up here. I ask the entire row to come up in one go. And that's exactly what happens inside your memory. Inside your memory, depending on the architecture, the cache lines are usually on the order of something like 64 bytes. So when you ask for a particular bit of data, you get the thing you wanted, say you, and you get everyone else on the entire row as well, because that's just how it works. So if you can come up with an algorithm that makes use of the 63 other bytes around the one byte you may have needed, then that's really useful, because then you don't have to keep going out to your warehouse on the other side of the planet to get what you need. Everything you just got in that one go is useful to you. So that's spatial locality. The things that you need next will be near the things that you have right now. The other thing that can be very useful when designing systems to make them fast is also temporal locality. If the things you need next are things you've used recently, that also really helps because they're already in the caches. So how can we create an algorithm or a data structure that uses adjacent data? Well, there is a data type in Java that does this by design. It's called an array. Arrays are really good, anything that uses an array underneath, because they are guaranteed to be laid out sequentially in memory. So when you grab something in an array, you get a lot of its neighbors as well. If you take an array and you wrap it to create a ring, basically you can scan along an array, and when you get to the end, you start at the beginning again because it has a bounded size. You can create something called a ring buffer. And you can create a data structure where you have several sections of the ring buffer. So at the moment, some of it's empty, some of it's being read, and some of it's being written. And at any one point, if you have threads communicating with each other, you need to figure out as to where the sections end and start. That's what we've done here. So this is a lot of code here. It's hard not to show this much code, but what the real key point here is not that you understand every line, it's the fact that now we're using arrays. Now, when you offer something to the buffer, what we're doing is we're iterating over all of the places that may have an existing value that matches it, such that we can replace one we've already got. And we do that linear scanning over an array, using our nice property we just learned about, the cache lines. If we find that we already have that key, all we do is we replace it. And remember here, we're not using any synchronized statement. We are quite simply using an atomic reference array, so we can use the set method on that, which is thread safe. Here is an implementation detail, not that important for what I'm talking about, but because these are happening concurrently, you need to, after you've done the update, you need to just check that this guy hasn't gone past it already. So if so, you have to add it to the front. This is what can possibly give you a few duplicates, but they're quite rare in practice. And you do the exact same trick on the reading thread. When you go over it, you read along an array. Again, you use that trick where the things that you need are next to the ones, the things that you need next are next to the things you have now. So again, we're using another array just to read. We find the index in the array. We null out the key because we no longer need it, and we add it to our bucket, and off we go. So how does that do? Whoa, that's a bit better, right? We got 1,000 times the performance of the original implementation by doing just this. So that's pretty good. That really helped. Let's see if we can do even better. Now, again, Like I was saying, the key theme is that if you understand a bit of what's going on the hardware level, it can really help you if you need to design high-performance systems. So when we compute the index in our circular array, what we need to do is we need to figure out the modulus of the index we're looking for with the capacity of the array. Now, it turns out that division and its cousin, the modulus operator, is one of the most expensive hardware operations you can perform out of all the operations that you're given on the chipset. So if you can get rid of this, you might be able to get some better performance. So how can we do that? Well, we can use an old trick, old computer science trick. Some of you may have come across it. What we can do is we can restrict our system such that the capacity has to be a power of 2. Yes, that puts a bit of a limit as to how big this can be, but in terms of if you care about low latency and performance, that might be worth doing. So we do this, we get the capacity, we create a bit mask where we just subtract 1 off the capacity, which is a power of 2, and then the compute index method looks like this. You're literally just bit masking the value you want with the mask you've created. Now, this might be going back a bit to your university days or whatever, and you can't remember exactly how this works. So let's have a quick look how it works, just to remind ourselves. So if we have 9, we want to divide by 8 and figure out what the remainder is. This is what we're doing. So our size in this case is 8, which looks like this in binary. We create a mask, which is 7, which we subtract 1 off this and create this, and it looks like that. And then what we do is our friend, the bitwise AND operator, right? We just bitwise these two things together. They're both high, both 1, so that ends up being 1. And those, because of the mask, just get those. And you'll see that this returns the exact same result as that. So by a single example, I've proven that this is exactly right. But yeah, that's how it works. So, and what do we get? Wow, okay, we get another good performance improvement by doing exactly this, right? Now we're at 34,000 COPS, which is the equivalent of 34 MOPS, if you like, of performance. Sounds pretty good, right? Okay, let's have another couple of looks at this diagram. What else can we learn by studying this diagram that will make this thing even faster? Well, there's this thing called the single writer principle, which is quite useful. As you see here, if we got if I got our producer running on this core and our consumer running on this core, the only way these can communicate, well, not the only way, but the fastest way they can communicate is over the L3 cache. So this guy writes some values to the data structure, to the memory hierarchy, puts it in here, goes into the L3 cache, and then this guy reads them. Now, one problem you can have is that if this core and this core are trying to modify the same cache lines, then they get in each other's way. They keep fighting over who owns the front row here in the cinema. And that's really slow. The hardware will work this out for you, but it's not good. Ideally, what you have is you give each row of the cinema to only one owner. There's only one writer for every bit of memory you have. That way, you can manage this contention, and all you're doing is you're publishing out updates from this guy to this guy. This guy never modifies them, he just reads them, and so forth. And that can give us some performance benefits. So how do we do that? What do we have to do in our code to make that change? Now, this is the exact same code as before. This first bit, all we've done is we've gotten rid of the thing that violated that principle. The problem was that when we were consuming data, this guy was cleaning up after itself. It was saying, okay, now we no longer need this thing, so I'll null it out so we can be garbage collected. And this is both true for the key and for the value. But that was the problem. That was causing the violation of the single writer principle. So if we get rid of this, right, and we don't do any cleanup, then we get a memory leak. So now we have to, now the producer, the guy who wrote the data in the first place, has to go clean it up when it can. So what we do is we add this cleanup hook on the producer side. The consumer just reads now. It doesn't clean up anything. It just reads it. And the producer, at certain intervals, at certain times, will call this cleanup method, and it will just literally go and have a look. What was the last thing I cleaned, and what's the last thing that this guy read? If they are not the same, then I've got some cleanup to do to follow this guy up. This is a bit like someone who's lazy who always leaves the kitchen dirty because there's only one person who ends up cleaning the kitchen. It's the person who cooks and cleans up. So this producer thread is the person who owns all that data and is the only person allowed to write to it. So the cleanup's been deferred. So what do we do? What do we get when we run that? Hey, wow, even better, right? Now we got 46 MOPS of performance. Right, that's pretty good. Let's dive back into the hardware one last time and see if we can do even better. Again, our favorite diagram. One thing we haven't talked about yet is these two guys. You see these two speech bubbles here. Each core has a load buffer and a store buffer, which it uses to communicate with the memory hierarchy over here. And what happens is, if you write something in this, it'll stay in this load buffer until it can be processed, and the hardware will just naturally keep draining these buffers for you. Now, if you do a volatile write, you're guaranteed that at the next instruction step, this publish has succeeded here. This is finished. So what it does when you do a volatile write, it will literally wait until this buffer is empty to guarantee you that the next step has been safely published to the memory hierarchy. And oftentimes you need it, but sometimes you don't. Sometimes it's okay just to stick the value you've just created onto this conveyor belt and just know that it will eventually get into the memory hierarchy and be seen by this guy. And when we say eventually, we're talking usually a few clock cycles. This is not long. But if you don't have to wait for every single bit of baggage you put onto this belt for the belt to be cleared again, you can potentially go much faster. So how do we do that in Java? How can we tell it, don't bother waiting till you've done it. I want you to be more lazy than that by using, and so this is the same code as before. We comment out this, this is the volatile. We used to write to this volatile to publish things out. Now instead, we use an atomic integer, or an atomic long in this case, and we use this lazy set feature that the nice guys at Oracle have given us that we can use to tell the hardware, yes, this needs to be published in order to the rest of the hierarchy, the memory hierarchy, but you don't have to wait till that buffer is drained. And when we do, and we can do the same thing here. Instead of eagerly setting this to null, we do a lazy set to null. So again, you don't have to, you're not stalling at any point for this buffer to drain. And if we do that, we get a bit more performance. Notice that we've exhausted some of the easy options to get more performance, and generally our rate of performance is slowing down. So there's a few more tricks that we've used to make this go even faster, and you can look at the source code, and it's all available. But at this point, we're going to stop. I think that's enough sort of tips and tweaks about what you're doing. One interesting thing, oh, that wasn't what I wanted. One interesting fact, for those of you who are still awake, is that on the x86 architecture, which most people run, the x86 architecture is a total store order architecture. So what that means is it never reorders writes with other writes. They do happen in order in the subsystem anyway. So when you do a lazy set, that is literally essentially just a normal write to memory like any other write. It is only true on the x86 architecture. On other architectures, that may vary. But that's part of the reason why you get a good performance boost from that. Oh, and by the way, the x86 architecture has some of the strictest memory guarantees of any architecture. That's why it's one of the easier ones to program for. So anyway, so we got to the end. We got some good performance out of it. We got there because we had ideas, we tried them out, and we measured them, right? We didn't just take some well-known mantras. We didn't just say, oh, this is fast, that's fast, we must do it, and just believe that it works. We got some ideas, we tried them, we measured them. Some worked, some didn't work. And at the end, we got something good. Now, there's one last step that can give you some performance improvement, and that's our friend over here. Anyone who knows who this is? Yeah, it's our friend Richard Stallman, right? It's the guy who wrote the GNU public license. The guy that gets very upset if any of you ever say the word Linux without putting GNU in front of it. So he is obviously the author of the GNU public license. And the way that can help you with performance is that we found that when we wrote this component, we published it, we made it open source, and then we had some very nice people who took their time to read what we published, looked over the source code, said, yeah, this is really awesome, but have you considered this? And some of those things that they said, have you considered this, were actually really good ideas. And thanks to some people who looked over our code, our performance got even higher because of some of the ideas that weren't our own. It's hard to believe, I know, but yes, there are some smart people out there, and some of the smart people will take time to look at your code if you open source it. So if you want even better performance, open source your stuff. I mean, it's hopefully getting more and more common. People do this. I understand that a lot of companies don't like open sourcing stuff, but it's not the absolute core competency of your architecture. It can give you some really good ideas, and I encourage you to try and push and open source some of the components you've written if you think other people will find them useful, because you will get benefit too. This component would not be as fast if we hadn't done this. So thank you, Richard. One more thing I'd like to talk about, and that is that a recent study has shown that the computing industry creates as much greenhouse gas emissions now as the global airline industry. and that survey was done before the Bitcoin miners started. So God knows where we are now. But the point is that efficient code isn't just fun to write. It doesn't a great opportunity just to come up here and talk about how awesome you are. It also can save the planet, right? Inefficient code uses up computing cycles. Again. Uses up computing cycles and is wasteful, right? Like my old colleague Martin Thompson used to say that, you know, go to a data center sometime, stand behind the servers where your code is running and feel the inefficiency of the code you've written, right? It's there. You can feel it. So that's another good reason to do that. So I've got a few links here. That's my blog. This is Martin Thompson's blog, an ex-colleague of mine. This is an excellent blog if any of you are interested in writing high-performance code. It's where pretty much all the ideas came from that built this. And if you go back there, you'll see all those principles explained in much more detail and more that I've just talked about. We have open source this component, so this is where you can find it. The example code I've gone through here, the full example code is available there, so you can see exactly what I was hiding from you there. And that's where I work, and we are hiring. So thank you very much. Thank you for sitting through the last talk of the day, and I'm happy to try and answer a few questions. Thank you.